I want to say that in the abstract I gave in the announcement, I say I'm going to consider several multifractal models. So probably I will be only focusing on one model. And the reason is that there was a very good overview talk in the second workshop, second work W2 of FDE by Stephen Saleh, who has introduced quite a few models in 30 minutes. So it's very good. It's a very good talk. So I invite everybody to listen if you're interested in this kind of stuff. So for me, I'm going to be focusing mostly on Levy processes. So there's one particular model which is multifractal. Okay, so that will be the focus, and I want to give a brief review, a brief overview of the topic, just to make everybody comfortable with the context and the notation and so on. So the multifractality comes from the concept of multifractality really comes from a paper of Frisch by Z in the 80s in their study of the turbulence, fully developed turbulence. So it is nowadays also found in many disciplines of science and technology, including astrophysics, finance, so just astrophysics, maybe finance, signal or image processing. Within mathematics, there's a dynamical system. Also functional analysis. Okay. Okay. Yes, go ahead. So very useful and popular subject, say. So in a nutshell, multifractal analysis is about the study of singularities. Study of singularities of functions. Of course, I need to define what I mean by singularities. And also the distribution of singularities, in the sense that we are interested in measure theory, measure theoretic properties of these singularities. So by that I mean Hausdorff of dimension, for instance, fractal dimension. Okay, so so just to make everybody just to make sure everybody is on the same page, so let me recall the basic definition of singularity that I consider, at least in this talk. So the first thing is what I call Holder exponent. So if you consider a function which is R, for instance, R to RD, and it's locally bounded, so that what I'm going to say makes sense. So alpha is a positive number. So we say f belongs to C alpha of a particular point. So it's a pointwise notion of C alpha space. If there exists a polynomial, say it's a polynomial, P with degree at most the floor function of alpha, integer part of alpha, such that if we subtract f, we subtract the polynomial P from F, asymptotically, when let's say when h is small, right? H is approaching 0. So actually, x is a fixed point. We consider x plus h when h goes to 0. If we subtract f, p from f, we have this this sort of power law behavior, this h to the power alpha, then we say the function. Okay, we say that the function belongs to C alpha X space if this condition, this local Holder condition is satisfied. Okay, so just a remark. So if alpha is smaller than 1, then one has to take a p equals to a constant, which has to be the value of f on the point x where x is fixed. In this case, we get back to the usual Holder condition. But this just allow us, this definition just allow us to consider alpha larger than 1. But then you need to subtract this polynomial, which plays the role of Taylor polynomial. So so P plays the role of Taylor. Okay, that's a simple remark. And now so that's what I mean by singularity, right? So and then we can define the so-called Holder exponent, because it relates to Holder space, which is for any point x, we define it as the largest alpha we can find, such that f, okay, alpha will be positive, such that f belongs to C alpha of x. The larger this thing is, the smoother, the larger alpha is, the smoother the function is, right? So we are interested in how smooth this function is. Just we call it a Holder exponent hf, which is the largest alpha such that f belongs to C alpha. It's a local definition because we only care about h goes to 0. All right, so with this definition in mind, this is what I mean by singularity. And I'm going to be interested in.
So supremum can it's possible that supremum is not maximum, yes?
Yes, yeah. Okay, so now I said I'm interested in, so go back to the previous page, I'm interested in measures the rank property of the singularity exponent. And by that I mean I'm going to measure the Hausdorff dimension, the so-called singularity spectrum, is the map H maps to Hausdorff dimension of the set of points, maybe x, such that hf of little x is equal to h. So we are given an order of singularity h, and we're interested in how large the set of singularity of a given order in the sense of Hausdorff dimension. Okay, so just to review, since I don't want to assume anything. So Hausdorff dimension is the notion. So first of all, I need to define what is so-called Hausdorff measure of a set. A is a compact set of RD, then Hausdorff measure is defined to be, if you take the infimum, if you take a limit, it should go to 0 and take the infimum of all the sum of the diameter of VI to the power S, I from 1 to n, and the infimum run over all the possible cover of A with diameter requirements smaller than equal to h. If you do this, this infimum will be monotonic if the limit exists. The limiting object is called Hausdorff measure of dimension S. It's the same thing if as the Lebesgue measure if S is equal to D. So reduce this to Lebesgue up to a constant if S is equal to D. All right. So the so-called Hausdorff dimension of the set, which can be found if you calculate the dimension of your, the Hausdorff measure of your set A in terms of the S, the parameter of your Hausdorff measure. We're going to find that is either infinity or zero, the Hausdorff measure, unless you are in this threshold value. This threshold value is called the Hausdorff dimension of your set B. Okay, so so far so good. Hope. Then the object of study today is the object. Okay. Today is Levy processes. And why we're interested in that? So because this actually provides among the first examples where the sample parts of the stochastic process are genuinely multifractal. And so one might ask, why not consider Gaussian processes, right? And the reason why we don't consider Gaussian is because of the following example. For instance, B is just a standard Brownian motion. And so by Levy's uniform modulus of continuity, we know that the supremum of B of T plus H minus B of T, T in 0, 1, for instance. So we consider uniform modulus of continuity, so H small of Brownian motion, and this is actually bounded by a constant times H log 1 over H. So we know that the regularity has a lower bound, which is 1/2, because it's this regular, so it has to be at least 1/2 for your Holder exponent. On the other hand, we have this fairly remarkable result of never able to pronounce correctly these names, Hungarian names. Churgo and Rivets. Okay. Their modulus of non-differentiability says that if you consider the minimum oscillation of your Brownian motion, supremum of U in 0, 1. So BT plus UH, you consider, it's still the oscillation. This is the oscillation. Uniform in time, and you consider the maximum oscillation in the interval of size H. And this guy is bounded from below by H divided by log 1 over H. So this one gives you the upper bound, this one gives you the lower bound, this one gives you the upper bound for the Holder exponent. So conclusion is that Brownian motion is boring in terms of their multifractal behavior. There's only one singularity exponent available. All the other values is just empty. The set that I want to consider here is just empty. So we have to go beyond the Gaussian. It's actually, this kind of law can be established fairly generally. So I'm going to give a remark or a reference. So a recent work of Xiao and co-authors, they have generalized this kind of uniform modulus from above and modulus of non-differentiability from below to fractional Brownian motions on more general Gaussian diffuse. So they are not very interesting from a multifractal standpoint, at least for this regularity exponent, the H.
One over H, yes. H is 1 over H.
That's the you mean
yes, in this case in fractional one.
Yes, that will be H. That will be just the first exponent, the regularity.
Don't worry,
yeah.
This Gaussian process is a single fractal dominant set, not multifractal.
Yeah, this is so-called a monofractal because there's only one fractal set. Well, it's not a fractal even, so it's just the whole image. All right. So this sort of brings us back to Levy process, which are very simple objects, probabilistic model. So what I mean by that, I think okay, first one is the introduction. So now Levy. Okay, so Levy process by definition are just the stochastic processes with values in RD is called Levy if it satisfies two properties. And first is that it has stationary increment in the sense that if I consider the process T plus H minus X of T as a process, so the parameter of the process H, it has the same distribution as just X H minus X0 as a process. So if you shift your parameter T, it doesn't change the laws. It's called a stationarity of this is called a stationarity of increments. And second property I want is the independence of increments, in the sense that if you have a T1, T2, Tn, I want to say that the family of random variables T n minus xtn, xtn minus xt n minus 1 x T2 minus xt1. So these are independent random variables. So the Levy process just satisfies characterized by these two properties, which is very natural. It turns out that one can have a more
continuity and probability. We need also continuity and probability.
Yes, I don't want to get into some too much technical details, but you're absolutely right. And but this is the essential properties that we use for handling Levy processes.
I think all of them are essential.
Also kind of Cadillac assumption.
I know you don't need Cadillac.
You can prove. I guess you can prove how you can find a Cadillac version because it's semi-quantum. Okay. Anyway, so these are the two properties I really use. I really make sense of. And what I want to say now is that there's a very amenable representation of Levy process. We call it a proposition due to Levy-Ito, called the Levy-Ito decomposition. So if X is a Levy in RT, then there exists sigma B pi where sigma is non-negative definite matrix, D by D matrix. B is just a vector in RD, and pi is a measure, is a sigma finite measure, such that this condition is satisfied. So this absolute value sign denotes the Euclidean norm in this talk. I want this integrability to be so actually there exists a measure such that this integrability condition is satisfied. And so what am I talking about? I can find a triplet like this, such that the process is written in terms of a scale, no, not scale. Well, okay, so some Brownian motion times the matrix plus a linear function in RD plus a small jump, the integral small jump x eta tilde dt dx plus 0t x larger than 1 x eta dt dx. So a lot of objects in one formula. So let me explain. So dt is just a Brownian motion, as I said, and eta is so eta dt dx is a so-called Poisson-Point process, or it can be viewed as a measure, sum of Dirac masses. It can be viewed as a measure or a set. So this is called a Poisson point process with intensity measure Lebesgue times pi dx. And by that, I mean, so a Poisson measure means that this guy is Poisson distributed with the measure of, take the intensity measure. Let me denote the intensity measure by lambda. You compute the volume of this of the set, and it's a Poisson distribution for any A. And also, if you have no overlapping disjoint, eta of A1, eta of AN are independent family. If you have a point process, okay, it's just a point process of random counting measure. If a counting measure satisfies these two properties, then it is called a Poisson. So it turns out that for Levy process, any Levy process, we can write it as Brownian motion plus a linear function plus, important part is here, plus a Poisson integral. So this is the easy part, where you have, this is actually a compound Poisson process. Since this is, as I told you, eta is actually a counting measure, the integral here is just a sum, right? So it's because it's the sum over Tx, which are in the support of my measure of this function x here. So this turns out to be a compound Poisson process. And the other piece, where you have only x less than or equal to 1, turns out to be a martingale. L2 martingale actually has moments of all orders. This guy here. The object defining this object requires a little bit of effort, but it can be done. And what is eta tilde? Just notation. Eta tilde is just eta, the counting measure, also random measure, minus its intensity measure with dt pi of dx. That's the tensor product of these two measures on the product space. So this guy minus is this is the so-called compensator. So once you have the object, you have an eta, you subtract it, you call it the compensated Poisson measure. And this guy integrate any function gives you a martingale, any function, okay, up to some integrability conditions. That's why you have a martingale here. This will turn out to be useful later. Okay, so now I have spent 25 minutes on just what is the Levy process. Are there any questions so far? Yes, there are experts in the audience. All right, so again, emphasize that Levy process is a Brownian motion constant. Sorry, linear function and compound Poisson process is really something like this, right? So it's like a piecewise constant function. And the tricky part really is to understand the local regularity of the sample pause is this thing with small jumps. So it's as very so just observation, not very deep, but it's useful. So we know that Brownian motion has Holder regularity 1/2 at every point. We know that the linear function is C infinity. Who cares about linear functions? And we know that the compound Poisson part is C infinity for all t, which is not in the set of jumps. So who cares about that? So really, the tricky part is, can we analyze the question? Can we analyze the local regularity? So the Holder exponent of the martingale part, or is the compensated Poisson integral part. Which is this guy here. So this will be the hero for the rest of the talk. Okay, so now move on to let me state the main result, right? So the main theorem, only theorem I'm going to talk about today, is due to it's a remarkable result of Rafah in '99 TRF. So it states that if you have a Levy process with Levy measure infinite, if Levy measure has total mass finite, then we just have a common possible process, and we know it's not interesting. So let's assume that it has infinite mass, and let this beta denote the so-called Brunel index, which is the infimum of gamma, such that the integrability condition is satisfied. Finite. Okay, so we know that. So here we only care about, because of the inf is 1, we only care about behavior, local behavior of the holder of the Levy measure around 0. So we know that this thing at 0 integrate x squared. X squared is actually much smaller than x gamma. So it could be that this I can integrate another function which is smaller, right? So I want to find the smallest possible gamma, and we call it the Brunel index because these are the guys proposing the index. Okay, let me give the name. Okay, so this index is very useful. And
from 0 to 2, yes, it is from 0 to 2.
From 0 to 2, exactly. That's the possible range for the Brunel index, absolutely. Because of the condition on the Levy measure, we know it's bounded by 2, right? So it could be as small as 0. We have examples. Okay, the result is following. So if you consider, there are 2 cases. The case 1 is that if your sigma is different from is 0, there's no Brownian motion, then what happens is the dx of h, recall that this is nothing but the Hausdorff dimension of the holder of the set of points with a given holder exponent h. So this is the regularity exponent, and this is given by beta h negative infinity. Beta is h is in between 0 and 1 over beta. You have a linear part, and you don't have anything. Hausdorff dimension equals to infinite is my convention of saying that the set is empty. So, this is I guess this is the most interesting part. I'm only gonna focus on this. There's no Brownian motion. If there's a Brownian motion, let me give you the.
So you mean for, almost surely that?
Yeah, almost surely. For all the h, you have dimension of this guy equals to beta h. And if I draw figure here.
So in particular, those sets are non-empty, yes.
These are the range from 0 to 1 over beta are not empty because you have a positive Hausdorff dimension all the way to 1 over beta. And 1 over beta has Hausdorff dimension 1. So actually the weight almost every point, this does not imply that, but I can tell you that the weight almost every point has Hausdorff dimension, has pointwise regularity 1 over beta. But there are the whole range of behavior, possible behavior for Levy sample points. And this is the dimension of the set such that hx of t is equal to given regularity h. So this is the case where you don't have sigma. If you do have sigma, the change is minor. So the threshold value now occurs at 1/2. Recall that since beta is in between 0 and 2, 1/2 is smaller than 1 over beta. So you have a threshold value here, which gives you pulse of dimension 1. And for all the h below 1 over 2, it's the same function. It's the same function with the same slope. The slope is equal to beta, the Mann-Coulter index. If sigma is different from 0, and the reason of this is just that when you have a Brunel motion, so whenever h, the pointwise regularity of your jump part is larger than 1/2, it's actually sort of killed by the Brunel motion, because if you have f is equal to C alpha, this very simple fact gives you the second spectrum. So if you have f belongs to C alpha, g belongs to C beta of x, then if you compute the sum, it's going to give you the smaller one, the roughest one, because the smooth one is actually bounded by the rougher one, the upper bound. So it's going to be the minimum of alpha beta. That's why we stop at this point, because for all the points more smoother than Brunel motion, it actually cannot be, the sum cannot be more smoother than Brunel motion. Okay, that's it. So I'm going to focus on this theorem only, this part of the theorem. Okay, so there are several steps. So elements of the proof. Okay, the first element is a random covering result. So here's the statement, my first proposition.
So this proof is from the paper you mentioned, or is it the
This, yeah, I only explained one paper, which is the paper with a file today. I'm going to give a proof of, depends on how much time I have, but I'll do my best to give as much as I can. I have the full proof, but
no, I was asking whether it is your proof or the original proof.
this is a slicker proof than the original paper. I did some improvement, but I'll mention that well, where are the difference in a minute. Okay, there's some arguments in the middle. Maybe I can tell you now because I don't have time to do everything. Okay, I'll tell you later. I have to tell you the context first. So the elements of the proof. So first, we want to know the pointwise regularity of Lévy process. We want to study the polar exponent. The first very useful criteria was very, I think it's a very smart observation of Jaffa in a different paper. Than his paper about Lévy. So this is I think it's Journal of Free Analysis and Applications. And so it says that if you have f, for instance, R to R Gadlog function. Okay, by that I mean it's right continuous with left limits on every point. And Gadlog function and J, the set of points where the jump on the point S, this is the set of jumps, okay? When J is dense. This is part of the assumption. Let's assume that J is dense. So we're in this situation because we consider the Lévy process where the possible measure is the infinite mass. So okay, so the sample function will satisfy this property. It's Gadlog and also dense set of jumps. Then for any Tn converging to T, let's say T is not the jump point of continuity, because we only care about polar exponent on the point of continuity. Then if this happens, then you can actually bound from above polar exponent by limit of n goes to infinity log of f of Tn minus f of Tn minus, this is what I call, sorry, I use my notation delta f of Tn, and divided by log of the distance from Tn to T. So if you have a dense set of jump, you have a sequence of jump discontinuities converging to T. Your polar exponent cannot be very good in the sense that it cannot be larger than this quantity here. So what is the reason of that? And it's just because we have a process, so a function. Let's say this here is my point T. The function jumps back and forth essentially very often at a certain rate, and this gives you the size of the jump. This is the delta f of Tn. And for T converging to T, Tn converging to T, you have this size jumps back and forth, so you cannot somehow find a concave function, to include everybody inside. That's basically the reason, and the proof goes by contradiction. You assume that's not true, use, but this is the reason. Essentially, reason is just this picture here. Okay, so that gives us the a very useful criteria for bounding from above polar exponent. So how are we going to do that in our situation? We have a Levy process. We know there's an underlying point process, the Poisson point process, which corresponds to the set of jumps in our case, for the Levy case, will be just those T's in the such that T of X belongs to my Poisson point process. It's in the support of my Poisson process, which is a counting measure, sum of Dirac masses. Okay. So this guy, if this one is belong to the support of beta, I record all the T. This gives me the set of jumps for the Levy process. And the following covering result will turns out to be useful. Proposition. Which is a theorem of its own. So if you consider eta be a Poisson point process on the product space with intensity measure, what you just considered, and if we consider the lim sweep set of the intervals, so these are okay. I used the I use Z to denote jump now. Consider interval T plus minus Z to the delta beta. So these are the intervals. What I mean by lim sweep for T, Z in my Poisson point process is that I consider all the set of times, maybe I should use another letter, S, for instance, 1, such that it's covered by this interval here infinitely often. So that's what we mean by lim sweep. Set of points which are covered infinitely many often by the set of intervals which is constructed from the jump time and jump size. You multiply, you compute the modulus, and then take to the power delta beta. You have an interval, right? Vertical points, compute the height, raise it to the power, compute the interval. So so that's infinite many often gets covered by the points. That's the notion of being close to the Poisson points. And this delta here actually quantifies how close we are to the Poisson points, because the set clearly is monotone in delta. Okay, the larger delta is, the set is closer in a way to the Poisson point process, to the jump points. Okay, so this is the set, very interesting. This is just a definition here. So what we actually want to prove is that almost surely, so for any delta smaller than 1, almost surely you have the full coverage. So this is the conclusion of the proposition. Conclusion of the proposition. So this actually says that the threshold value for having full coverage of the interval 0, 1 occurs at 1. For all the smaller values, you have coverage. For larger value, the set gets smaller, you don't have coverage. Right? So the threshold value is at 1. How are we going to prove this? So the idea is to use a discrete approximation of what we just claimed. So I'm going to cut my interval 0, 1 to little pieces of size essentially 2 to the n times beta, but I need some little room for the proof to work. Actually, I'm going to take n to the alpha, which alpha is slightly smaller than beta, right? Beta minus 2 epsilon. And since delta is smaller than so first we fix delta less than 1, we can then find epsilon small enough so that alpha is still larger than this time. Okay, so but essentially think of it as just beta. So this is my time scale. And vertically, we're going to have this, this Poisson point process. Here is considered this as RD. This is just R, actually 0, 1. RD, okay, forget about D. Let's just say it's R. And we want to also decompose, cut it into different pieces, consider different scales. The scale is 2 to the negative n, 2 to the negative n minus 1. All right, so the goal will be to find in every little box, so box size is 2 to the negative n alpha, and the height here is 2 to the negative n, 2 to the n minus 1. So, so essentially 2 to the negative n, the jump size is essentially 2 to the negative n, and the time in the small interval. The goal is to find precisely, not precisely, but at least 1 point in each of these intervals. If you can find in 1 point, at least 1 point in each of the intervals, this is the height, right? So that's give you 2 to the negative n. If you raise to the power of beta delta, and that's the thing you have in your small intervals, and this is sufficiently enough to cover this quantity because of the choice we made about alpha. As long as we can show that infinitely often at scale 2 to the negative n, I can find a point in any small interval of size 2 to the negative n alpha, I win, right? So that's the goal. And in order to show this, it's a simple Poisson estimate. We just consider the event En, which says there exists a k. I consider the complement of my events, which is that n 2 to the, sorry, there's no n. So 2 to the n alpha. So this notation means the set of integers from 1 to this number here. I consider all the it's not dyadic, so all the intervals at the time scale. And I'm going to say that I cannot find anything in my small interval. So this interval will be called Dn, and each one of them will be called Ink. There exists a case such that there are no point at all in this window. What is the probability of this? So the probability of this, if you use unit bound, is just 2 to the n alpha, number of intervals. And each individual probability is just the probability of a possible random variable equal to 0. And that is given by exponential to the negative, the size in terms of the measure, the lead measure of that. And it's the product measure, okay? So the length of this guy is 2 to the negative n alpha. And the measure of this guy is just, pi of dn. Okay, so here is what we use the definition of multifractal index. 5 minutes, okay. I'll finish the proof and I'll stop here maybe. Okay, 2 to the negative n alpha. If you use the multifractal index, so this guy is essentially 2 to the n beta, essentially. Okay, up to some epsilon in the power. So for infinitely many n, this doesn't hold for all of them. But for infinitely many n, we can actually find for infinitely many n, we can actually find this guy actually have a lower bound like this. So then you can use multifractality lemma, take the sum over n, so that this actually implies by multifractality lemma. This actually, because this thing eventually will be summable. So it's going to be e to the sum 2 to the n epsilon. Choose the epsilon wisely. So this guy really goes to 0 very fast. So it's summable in n in such a way that the limit sweep event occurs. It's probably 0. So the complement of this actually gives us the what we want, right? So all the n large, all the k, all the dyadic intervals, not dyadic, but okay, so this kind of intervals, there is at least one point in my window like this. You have infinitely many scales, tiny and tinier. You can find infinitely many scales such that for every interval, smaller and smaller intervals, you can find exactly, okay, at least one point, and that gives you the coverage you need, which concludes the proof. Okay, that's the, I want to give a consequence of this before I finish. The corollary is that almost surely, so hx of t is bounded by 1 over beta for all the t from 0 to 1. So this explains the support of the singularity extreme. It cannot be larger than 1 over beta. And that's just because for any delta smaller than 0, smaller than 1, so we have the proposition, the criteria of Jafar says that, you can find hf of x is bounded by a limit of the size of jump, log of size of jump divided by log of distance from the jump point to t. And we have just proved that where are these jumps? So we can find at least one jump at this scale. So this scale, you see this scale 2 to the n, this is the scale, the point distance will be 2 to the negative n. So that gives us 1 over alpha power for the upper bound. So 1 over alpha is actually just 1 over beta delta. That's what we have. And since this works for all the delta less than 1, so this we conclude that HF is bounded by 1 over beta by letting delta equals 1. And this concludes the proof of the corollary. Can I use 2 more minutes? All right, so maybe 1 minute, right? So I just want to give a sort of a punchline of the the talk. So this is only upper bound. This does not tell you much, right? So this tells me, okay, the range has to be 0, 1, or beta. So why it has a particular behavior at every possible value in the whole continuum set, 0, 1, or beta. And the reason is that you can repeat exactly the same argument. If your t is in A delta, you change your delta value, you realize that, so this is the deterministic statement. If you are in this set, you have this many jumps and that close, and you have an upper bound of this type for any delta larger than or equal to 1. So now we consider delta larger than 1 because less than 1 you have whole coverage, okay? Every point is that close to the jumps. So if we want to study Rothford regularity, you have to go to the points which are closer to jumps. That's why I consider delta larger than 1. So if a delta larger than 1, you always have this upper bound. It gives you actually a smaller and smaller, because delta is larger than 1. This gets smaller and smaller than 1 over beta, can be as worse as 0. If your delta is go to infinity, for instance. So so this turns out to be the case. We can prove it by using proof using the original proof of the file used some estimates about empirical processes, and there's a martingale proof, which is what I'm talking about, the slicker proof. Gives you a faster way of getting exactly the same kind of estimate. Because we so I'm talking about the lower bound, sorry. This is the upper bound, and the lower bound also works. So that in the end, what happens is that you can find, the punchline is this. If you can find for any t, you consider how close you are to the point, you find the optimal delta such that you belongs to a delta. It's a decreasing set, you stop at some point because in the end you don't have anything. So stop at the largest delta you can get for each t, and this guy actually characterized the Holder exponent of your Levy process at every point of continuity. And I think I can stop here. Thank you very much for your attention.
Thank you, very nice talk. Just a question a little beyond it. So if you consider stochastic differential equations driven by this pure jump but without big jump Levy process,
yeah,
would the properties kind of be the same?
It's a very good question, and this is part of my thesis, my PhD thesis. Was published already. So the theorem said if you have, for instance, you can consider this sort of generator. For 2, I guess. Negative sign. So if your generator is something like this, you have a pure jump Markov process. And this Markov process, you can truncate the large jumps you want, but you can keep it. They don't contribute anything anyway. And if you consider this, the multifractal spectrum is very different from what you get for the pure jump Levy process. So if you, so essentially you have a range of behavior for the Brunel index, and eventually the spectrum looks like this. Hausdorff dimension of your set of singularities, h of x, hx of t is equal to h, is given by this. The thing looks like a fractal itself. So it's the superposition of line segments which corresponds to beta of xt. This solves, okay, to answer your question, this actually solves the stochastic differential equation, an SD with pure jump process. So this one can have much different multifractal behavior in So general Markov process, you can really expect to have more complex multifractal things.
Thank you.
So I have two questions.
Yep.
So the first one is about subordinators.
Yeah.
Is there any intuition that you can give us on the conjecture that the behavior of the path of subordinators is related to the Bayesian staircase? And this is my first question.
Yeah.
The second question is considering multifractal spectra. So if you consider the empirical multifractal spectra taken by applied scientists, their behavior is usually something like that. So it's a sort of parabolic or distorted parabolic, etc. Whereas the Levy processes give this behavior here. So, so some empirical, some applied scientists say that this is a reason for not using Levy processes in modeling. And what is your take about this?
Okay, so come to the first question is about spawnator.
Yes.
So spawnator, you said you want to compare this with a Devil's staircase.
Yeah, the staircase is deterministic.
Because that's the inverse of one or another. So okay, you know this already. So then, what should I say? So the proof I gave here really does not depend. You can consider jump process, which is pure jump, it's just increasing process, a spawnator with infinite jump activities. Then the whole argument does not rely on anything like this. So it's really that if you have a dense set of jumps, and this deterministic criteria which I found gives you an upper bound for the Holder exponent. And since you can be in a way close to jumps at a certain order or another order, then you can have different kind of Holder exponent, like what I just said here. So it's this thing really works with any log function. So well, inverse of this is gives you of course the inverse of this gives you so-called local time, or that was staircase, but I don't see, well, they can, you can say some things about it, like the range of the horizontal dimension of the range of spawnator corresponds to the point of increase of your Devil staircase. That's a local time, so you know you can do some regularity estimates for local time. You can find estimates for the horizontal dimension. Okay, so second question is about what again?
Yes, it's about comparison between the empirical.
Yes. So maybe it's not so empirical because just the Frisch by the formalism. Which says that if you consider discrete quantities, you have a function of a signal, you consider this LP type estimate in 01D, for instance. The X LP type, and you scale it according to little h. It's going to be a function of p. So you scale it, and this somehow is can be related to the multifractal spectrum I consider in terms of horizontal dimension, the Holder exponent and so on. And this, at least in some functional spaces, has been proved by Jafar in resolved spaces. So quasi all the functions of in resolved space satisfy sort of the link between the average quantity with the quantity I mentioned in my D function, my multifractal spectrum. Let's use some Laurent transform. This is actually holds in a large class of functions in general, and quasi every function satisfies this identity there. So I think for Levy, you always find this either for Levy you have a straight line. For more general Markov, we might have something like this, but it's never something like a cup function. But you have other models which correspond to cup functions, like the multiplicative cascade,
Yes.
Monte cascade. Then you have a whole class of stuff, GMC, Gaussian multiplicative. So they all give you this cap-shaped multifractal spectrum. I think one question posted by Stefan in his talk about multifractal, one of the discussion session, second workshop, is that to find the natural stochastic processes, because cascade is actually a measure, kind of stochastic processes such that you can cook up a process satisfying, but the natural one, you can always construct something with, for instance, wavelet number. You can find a wavelet series, random wavelet series. You can do everything with wavelet. So you can have this, but maybe that's not very natural. Is there a natural stochastic processes such that you can find this kind of cup-shaped spectrum? That's open.
This is open.
Yeah.
Can I comment? Actually, the relation between this scaling function, which you denoted tau of P or Q,
Yeah.
and the multifractal spectrum is just Lejeune transform.
Yeah. Exactly.
Lejeune transform of this function
Yeah.
in multifractal spectrum, and it is known that Lejeune transform is convex function. So
Yeah.
it means that. So it means that you are looking somehow outside of this formalism, multifractal formalism. And on the other hand, there are examples when we can obtain from the multifractal products spectrum of this type. I sent it basically,
Yeah.
and they can be constructed as kind of rescaled products. So I mean that the philosophy, sorry, is like, I mean, if you from the sum you can obtain some similar object, and from the product you can obtain multifractal object, and it is possible. And also in this theory, there is a negative part of the spectrum, which is also very interesting from the point of view.
Yes.
So somehow the processes are multifractal, but somehow they're not main examples. So, well, that's probably
that's probably the first example because it's so simple. The process is so simple, and it's multifractal. Turns out to be.
Multifractal, but somehow not naturally multifractal in some sense, maybe, because of again, multifractal spectrum must look in some form of.
Not necessarily, right? So because I consider multifractal in the sense of to consider dimension.
Depending
Type,
on the definition,
dimension,
yes,
fractal dimension type multifractal. Then that's when you study singularity, this matters. When you do oscillation, when you do simulation or numerics, then of course in applied science, then you want to take average because you never be able to measure the pointwise regularity precisely given data, right? So that's why you do the other way.
In this way, you could have a negative part. There is a kind of one part is a kind of positive part, and another part for a negative moment. And you cannot say anything for a negative moment in this methodology.
Yeah. Agree.
Okay, so.
I have one last question. Can you say something about numerical schemes? For instance, these empirical experiments, if you want to estimate the scaling exponent.
Yeah.
More appropriate, something like that.
Numerical schemes.
Algorithm method.
In terms of numeric, I guess you can somehow this thing here, if you take some average kind of quantity, this already can be very easily implemented. So you can do all the increments to take the sum. This is essentially a sum, right? So if h is equal to 2 to the n, then you take essentially you take the sum over k from 1 to 2 to the n, small interval size 2 to the n, to the negative n, and then you have an increment of f. So I should actually use this. The increment f in the dialectic interval, so I and k, to the power p. This is an easily calculatable quantity for every p, and you try to do this for to find the log scaling, log regression in terms of p. Then you can find this exponent here. Jolly exponent, you can take Lorentz transform things that gives you something. As to say about.
There is a base empirical moment, which is measurable. You know, and the consistency of large numbers. And then they invoke you obtain exactly.
For example, in the nuclear, there are some wavelet.
Wavelet is, yeah. There are wavelet exponent as well. All sorts of things. So, yeah, there's a large body of work. We, for instance, work a lot with Raphael. They together develop a lot of numeric methods using wavelets in multifractal models.
Discussion, I think.
Yeah.
Let's thank the speakers once again.